Hello, welcome to this channel. I'm Mehdi, and in this video we are going to talk about the pattern allowances in casting. Let's go over the types of allowances considered in casting. Well, patterns play a critical role in the casting processes. They are crafted from wood, metal, or other materials, and often feature colors distinct from the final cast. This material choice is intentional, as the pattern doesn't necessarily need to match the casting material. It simply shapes the mold. Now, patterns are specially designed with additional allowances. These allowances compensate for different factors affecting the final cast. The primary purpose of these allowances is to counteract metal shrinkage during cooling. If we were to make the pattern exactly the size of the final cast, it would result in a much smaller casting. So, pattern makers built in a specific percentage to account for this shrinkage. Patterns also come with machining allowances. After casting, machining is typically required for a smooth surface finish or exact dimensions. This means the initial pattern is slightly larger to allow for this post-processing. Another important feature is the draft allowance. Patterns have slightly tapered sides. So when we pull the pattern out of the sand, it doesn't damage the mold walls. Without a draft, the mold might crack or pattern could even get stuck. The pattern's shape also includes distortion allowances. Because metals can wrap or bend slightly as they cool, pattern makers offset this by making certain parts of the pattern slightly out of alignment, so that once cooled, the casting has the desired shape. Patterns may also have core prints. These projections allow space for the core, which helps create internal cavities or hollow sections in the casting. With core prints, we ensure the core sits perfectly in place, aligning with the other mold features. Patterns are often made in multiple pieces, while the casting itself will be one solid part after cooling. Sharp changes or intricate details are avoided in the pattern, since they are easier to add later through machining. Shrinkage allowance is essential in pattern making due to the significant contraction that most metals undergo when cooled from a molten state. The total volume contraction occurs in three stages. Stage 1, liquid contraction. As the molten metal cools from its pouring temperature down to the liquidus temperature, it contracts. This shrinkage happens while the metal is still fully liquid. Number 2, solidifying contraction. Next, as the temperature drops from the liquidus to the solidus temperature, the metal begins to solidify and continues contracting. Number 3, solid contraction. The final stage of contraction happens once the metal is fully solid and cools further to room temperature. This stage, called solid contraction, is what pattern makers address by applying a shrinkage allowance. The first two contractions are managed with appropriate gating and rising techniques to ensure consistent metal flow and minimize defects during the pouring process. However, for the last phase, solid contraction, a positive shrinkage allowance is applied directly to the pattern. This shrinkage allowance changes by metal type because each metal contracts at a different rate. For example, cast iron contracts by about 10 millimeter per meter, while steel contracts at a rate of 21 millimeter per meter. To account for this, pattern makers use a specialized tool known as a contraction rule or shrink rule. This rule resembles a standard ruler but is slightly larger with dimensions tailored to each specific metal's shrinkage factor. This ensures that the pattern compensates for the metal solid contraction, resulting in a casting that matches the desired final dimensions. The contraction rules adjustments are essential for casting accuracy, specifically for materials with high shrinkage rates. In casting, we add what's called a machining allowance to ensure the final part meets its intended dimensions after machining. Since materials is removed during the finishing process, without this extra material, the casting could end up undersized. The amount of machining allowance depends on a few factors: the size of the casting, the specific machining techniques used, and the desired quality of the finish. Typically, it ranges between 3 to 18 millimeters. This allowance makes sure that there is enough material on the casting so that after machining, the final dimensions are precise and meet specifications. Well, draft or taper allowance is an intentional adjustment applied to all vertical surfaces on a casting pattern. This allowance creates a slight angle, making it easier to pull the pattern out of the mold without damaging the mold walls. The usual taper for external surfaces is between 10 to 20 millimeters per meter, while smaller internal features like hole and recesses might need a steeper taper, around 60 millimeters per meter, to account for their tighter spaces. The size of the pattern and molding method also influence these values. For machine molding, for example, the draft angle might vary more from 10 up to 15 millimeters per meter. This taper ensures a smooth pattern release, which is crucial for maintaining the mold's integrity and the casting's final dimensions. Right. Wrapping or shake allowance is an adjustment made to account for the slight changes in mold cavity size that happen when the pattern is loosened before removal. To release the pattern smoothly, it is gently tapped or wrapped, which shifts the mold cavity. This movement makes external sections of the mold slightly expand outward, while internal sections shift inward. So minor in smaller or medium casting, this shift becomes more pronounced in larger castings. To balance this effect, wrapping allowance is generally negative, meaning the pattern dimensions are slightly reduced, usually by about 0.5 to 1 millimeter. This ensures that the casting dimensions remain accurate once the mold is fully prepared. Okay, how about distortion allowance? It is used for casting that tend to change shape during cooling. This shape change or distortion happens because thermal stresses build up unevenly as the metal cools. So, take a U-shaped casting as an example. As it cools, the closed end contracts, while the open end remains relatively fixed, causing the legs to spread apart. To contract this, we apply a slight convergence to the legs in the pattern. By adjusting the pattern this way, the legs of the U shape will end up parallel after cooling, resulting in a casting that holds its intended shape. This allowance is key for complex shapes, ensuring that thermal stresses do not alter critical dimensions or alignment. And finally, mold wall movement allowance is applied to compensate for slight shifts in the mold walls during casting. In sand molds, mold walls can move slightly due to the heat and static pressure exerted by the molten metal. This effect is particularly evident in ferrous casting, where expansion occurs because of a process called graphitization, which causes the metal to expand within the mold. The degree of this mold wall movement depends on factors like the density and composition of the sand, as well as the moisture level and temperature at the mold-metal interface. As moisture and temperature increase, so does the likelihood of mold expansion, which can enlarge the mold cavity and alter the casting dimensions. By applying this allowance, we account for any shifts that could impact the final casting accuracy. That was a quick overview on pattern allowances in metal casting. If you have any questions or want to learn more, feel free to ask in the comments below. Thank you for watching. If you found this video helpful, please like and subscribe for more insights. I'm looking forward to sharing more with you in future videos. See you next time.